On the morning of February 12, 1947, the Sikhote-Alin mountain range in eastern Siberia was locked in deep winter. Snow covered the forest, temperatures were well below freezing, and the region was sparsely populated by loggers, hunters, and small rural settlements. At approximately 10:38 in the morning local time, that quiet routine was shattered by a sudden, blinding light that tore across the sky. Eyewitnesses described a fireball so bright it rivaled the sun, forcing people to shield their eyes or turn away in fear. The object streaked from north to south, leaving behind a thick, white smoke trail that twisted and expanded as it drifted in the cold air. Moments later, a series of thunderous explosions echoed across the mountains, loud enough to rattle windows and knock people off their feet. Some observers reported feeling a wave of heat on their faces despite the freezing conditions, a result of the intense energy released as the object tore through the atmosphere. What made this event especially terrifying was how low it happened. The fireball did not burn up quietly high above the Earth. Instead, it penetrated deep into the atmosphere before violently breaking apart. As it fragmented, glowing pieces peeled away from the main mass, continuing toward the ground at extreme speed. To those watching from below, it looked as if the sky itself had shattered. Then came the fallout. Metal fragments began raining down over the forest, crashing through tree branches and slamming into the frozen ground. The sound was described as roaring, cracking, and whistling, followed by heavy impacts that sent tremors through the earth. In some areas, the falling debris ignited small fires as it struck dry wood beneath the snow. For hours after the explosion, a long plume of dust and smoke hung in the sky, stretching for tens of kilometers and slowly dispersing in the winter air. People across the region knew they had witnessed something extraordinary and deeply unnatural. Unknown to them at the time, this was the largest witnessed iron meteorite fall in recorded history, and the beginning of one of the most important scientific investigations of the 20th century. When the explosions finally faded and the sky began to clear, the true scale of what had happened in the Sikhote-Alin Mountains slowly revealed itself. Deep within the Taiga, an enormous stretch of forest had been violently transformed. Trees were snapped, stripped of branches, and flattened in chaotic patterns that pointed back toward the sky. The ground itself was scarred, punched, and torn open as if struck by artillery fire. The meteorite fragments did not land in a single spot. Instead, they were scattered across an elongated, elliptical impact zone measuring more than 1 square kilometer. Within this area, scientists would later document well over 100 impact craters, ranging from small fist-sized pits to massive gouges in the frozen earth. The largest crater measured roughly 26 meters across and plunged more than 6 meters deep, its edges sharp and raw from the force of impact. What puzzled early observers was the strange relationship between crater size and fragment size. Some of the largest craters contained only tiny pieces of metal, while smaller craters sometimes held massive chunks weighing hundreds of kilograms. The forest floor was littered with twisted iron, shards, jagged slabs, and compact metallic masses, unlike any rock native to the region. Many fragments were still partially embedded in the ground, surrounded by splintered roots and frozen soil thrown outward by the impact. Local residents and forestry workers were among the first to reach the area. They described the scene as resembling a battlefield, with metal scattered everywhere and trees damaged in all directions. The fragments were astonishingly heavy for their size, instantly setting them apart from ordinary stone. Some pieces showed sharp, torn edges, as if ripped apart by extreme force, while others appeared smoother and more rounded, darkened by intense heat. Within days, news of the event reached scientific authorities. Reports of metallic debris falling from the sky, combined with eyewitness accounts of a massive fireball and explosions, made it clear this was no ordinary atmospheric phenomenon. The Soviet scientific community quickly realized the importance of the site. Preparations began for an official investigation, as researchers understood they were dealing with an exceptionally rare and well-preserved meteorite fall. The Sikhote-Alin forest had become a natural laboratory, frozen in time. Every crater, every fragment, and every damaged tree held clues about the object's violent descent. What caused such a powerful breakup, so close to the ground? And what exactly was this mysterious iron raining from the sky? Those questions would soon drive one of the most ambitious meteorite expeditions ever undertaken. As reports from the Sikhote-Alin impact zone continued to pour in, the scale of the event became impossible to ignore. Later that same year, the Soviet Academy of Sciences organized a full-scale scientific expedition to the remote crash site. The mission was led by Akademician Burdunsa Vladimir Grigorovich Fesenkov, one of the leading astronomers of the era, and it marked one of the most ambitious meteorite investigations ever attempted. Reaching the site was an ordeal in itself. Scientists traveled by rail to the farthest accessible settlements before continuing on foot, skis, and sleds through deep snow and rugged terrain. Supplies had to be hauled across frozen ground and progress was slow. Once in the impact zone, the team established field camps and began the painstaking task of mapping craters, cataloging damage, and recovering fragments scattered throughout the forest. A crucial part of the investigation involved collecting eyewitness testimony from villages spread across the region. Hundreds of people had seen the fireball streak across the sky, heard the explosions, or felt the ground tremble. By comparing the timing, direction, and intensity of these reports, researchers were able to reconstruct the meteorite's flight path through the atmosphere. This data allowed them to determine the angle of entry and the general direction the object had traveled before breaking apart. As fragments were collected and examined, scientists noticed a clear pattern. The recovered material fell into two distinct categories. One group consisted of sharp, jagged pieces with torn edges, often twisted and irregular in shape. These fragments showed signs of violent mechanical breakup, indicating they were ripped apart during the low-altitude explosion or shattered upon striking the ground at high speed. The second group looked very different. These pieces were more compact and rounded, with smooth, darkened surfaces. Many displayed shallow, thumbprint-like depressions, formed as their outer layers melted and ablated during flight. These features revealed that some fragments had separated earlier and traveled longer through the atmosphere, slowing down before impact. This discovery was a breakthrough. It showed that the Sikhote-Alin meteorite did not simply explode once, but fragmented in multiple stages during its descent. Each stage produced different types of debris, leaving behind a complex and revealing pattern on the ground. Over successive expeditions, scientists would recover more than 23 tons of material, creating an unprecedented collection for study. What began as a terrifying spectacle in the sky had now become a meticulously documented scientific event. With eyewitness accounts, now crater maps, and thousands of kilograms of recovered metal, researchers finally had the evidence needed to answer the most important question of all. What exactly was this object, and where did it come from? With thousands of recovered fragments now in laboratories, scientists could finally focus on the meteorite itself. Detailed chemical testing quickly revealed that the Sikhote-Alin object was an iron meteorite, not a stony one. Its composition was dominated by iron, with a significant amount of nickel, along with smaller traces of cobalt, phosphorus, and sulfur. This explained why the fragments were far heavier than ordinary Earth rocks, and why so many pieces survived the violent descent. When researchers cut and polished several specimens, an extraordinary internal structure appeared. Etching the metal with acid exposed a distinctive interlocking crystal pattern known as the Widman-Staughton pattern. This structure can only form when molten metal cools at an incredibly slow rate, measured in degrees per million years. Such conditions exist deep inside large asteroids, but nowhere on Earth. This pattern provided definitive proof that the Sikhote-Alin meteorite originated in outer space and was once part of a much larger body. Using trajectory data reconstructed from eyewitness reports, shockwave timing, and crater distribution, scientists calculated the object's path before it entered Earth's atmosphere. Their results showed that the meteorite had been traveling on an elongated orbit around the Sun. This orbit traced back to the asteroid belt located between Mars and Jupiter, a region known for frequent collisions between large rocky bodies. The evidence suggested that the Sikhote-Alin meteorite was a fragment from the metallic core of a parent asteroid that had been shattered in a collision millions of years earlier. Over vast spans of time, gravitational interactions slowly altered its orbit until it crossed Earth's path. What fell over eastern Siberia was not just a random space rock, but a remnant of an ancient planetary building block. This realization marked a major scientific milestone. For the first time, researchers could directly connect telescopic observations of asteroids with physical samples recovered on Earth. Sikhote-Alin became a critical link between cosmic theory and tangible evidence, proving that meteorites are literal pieces of other worlds. By the end of the analysis, the event was no longer just a historical curiosity, but a cornerstone in the study of planetary formation and near-Earth hazards. This Sikhote-Alin meteorite fall remains unmatched as the largest witnessed iron meteorite event in recorded history. Scientific estimates suggest the original object weighed close to 100 metric tons before entering Earth's atmosphere. Even after the violent breakup and airburst, tens of tons of material survived and struck the ground, an extraordinarily high survival rate compared to most meteorite events. This sheer mass is what made the event so scientifically valuable and so physically destructive. Unlike stony meteors that often disintegrate completely, the dense iron composition of Sikhote-Alin allowed fragments to reach the surface at tremendous speed. This created a crater field unlike anything previously studied in real time. Researchers discovered an unusual pattern during excavations. Some of the largest craters contained only tiny metal remnants, while smaller craters sometimes held massive chunks. The conclusion was striking. The largest fragments hit with such force that they partially vaporized on impact, while smaller pieces slowed enough to survive intact. When scientists compared Sikhote-Alin to other historic cosmic events, its uniqueness became clear. It released less total energy than the Tunguska explosion of 1908 and far less than the Chelyabinsk airburst of 2013. However, neither of those events delivered anything close to the amount of recoverable material that Sikhote-Alin did. This made it a once-in-a-lifetime natural experiment, allowing scientists to study crater formation, fragmentation physics, and atmospheric entry behavior using real-world evidence. The meteorite also reshaped how scientists understood asteroid threats. Sikhote-Alin demonstrated that iron-rich asteroids behave very differently from stony ones during atmospheric entry. This insight became crucial for later planetary defense models, helping researchers predict how different types of near-Earth objects might break apart or survive if they were ever on a collision course with our planet. Today, Sikhote-Alin fragments are housed in major museums and research institutions around the world. Some pieces still bear sharp, torn edges from the explosion, while others display smooth, sculpted surfaces formed during flight. Each fragment is a physical reminder that Earth is not isolated from space, but part of an active and evolving solar system. The fall of the Sikhote-Alin meteorite was not just a strange event from the past. It was a turning point in planetary science, proving that cosmic disasters can be studied, understood, and prepared for. Long after the smoke trail faded from the Siberian sky, the impact of that iron rainstorm continues to shape how humanity looks upward, knowing that pieces of the universe can, and sometimes do, fall straight into our world,